Day 39, Honors Physics, Newton's 3 Laws, Example 45. I have the free body force diagram for the 5 kilogram mass while it sits on a table and it's at rest. We have an unknown mass right now hanging over the side of the table. But if it's all at rest, we have a static situation. The force of friction is static, so it matches the tension. It says what weight is required at the end of the cord in part A here to get this 5 kilogram mass to move. Well, that basically involves figuring out the maximum frictional force and then exceeding the maximum frictional force with our pulling force T. So let's figure out the maximum friction force. Friction force static. Its maximum value is when we have it equal to the static frictional coefficient times the normal force, F sub n. So its maximum value, I could have said maximum here, F sub F maximum is, let's see, what's the coefficient of static friction here? 0.40. So 0.40 times 50. So the maximum frictional force is, I believe that's 20 newtons. So that's how much weight we need to get this to go. In other words, if you put a 20 newton weight, which has a mass of 2 kilograms, it says what weight? Well, it says what weight is required. So we need a 20 newton weight. That's the answer to part A. We need 20 newtons of weight hanging over the table to have any chance of getting this thing to move. Anything less than that, friction will match it. But that's the initial condition. Now it says in part B, what is the acceleration of the block once it starts to move? So if you put a 20 newton weight on there, things have to be reset in a sense. Things will accelerate. And here's the part that is a little confusing the first time through this. Once this whole system starts to accelerate, the tension in the rope that connects the two changes from what it was. When it's stationary, the tension in that rope is equal to the weight, like we just did there in that problem. When it's just sitting at rest, when everything's sitting at rest, that weight that's hanging over the table, in this case is 20 newtons, or let's say it was 19 newtons, the string or the tension in the rope would be 19, the weight would be 19, so everything's at rest for both objects. But once it starts to accelerate, you have to draw new free body force diagrams like this. And we had a problem, someone like this before, but we had this simple one with no friction. But we have the 5 kilogram mass. I'm going to draw this. So here's the free body force diagram for each of the two blocks in part B. Once again, to reiterate, in part A, when nothing is moving, right, when it's at rest, the hanging block, which was 20 newtons, would have a tension above it of 20 newtons, and the string itself has an equal tension everywhere, so the tension was 20 newtons, so the force of friction was 20 newtons. Everything was 20 newtons. Or 19 newtons, all of those would be 19s, 19, 19, 19, 19, or 15, 15, 15, 15. But at 20 newtons, the whole system now starts to accelerate, so everything changes. The force of friction changes, the tensions change, they're no longer 20 because you're accelerating. So let's start with the force of friction. Now it's kinetic friction, so we can calculate that. There's never a less than or anything less than equal to, it's always equal to. So the force of kinetic friction, force of friction, is mu times normal force. So we know the coefficient is 0.25 and the normal force is 50. So the force of friction is 12.5. Since I've been doing rounding off already, I'm going to round it off to 13 newtons. So the force of kinetic friction is 13 newtons. It's not 20 newtons. So that changes everything. It changes the tension in the string. Even though the tension in the string is the same for both objects, the tension pulling up on the 2 kilogram mass is the same as the tension pulling to the right on the 5 kilogram mass. They're not 20s. All right? You'll see that play out here as we go along. We're going to apply F net equals ma to each of the two masses and solve the system of equations. So for the one on the table, I'll use black for that one, F net equals ma. F net is the bigger force. It's going to accelerate to the right, so T is the bigger force there. So it's T minus the force of friction, which is 13 newtons, equals that mass on the table, 5 times A. For the hanging mass, I'll use blue, F net equals ma. Now in that case, that one's accelerating down, so the downward force is bigger than tension. So the tension is somewhere between 13 and 20 newtons. You'll see that as we go out and we go more later on in the problem. But F net is the big force, 20 minus T, big force minus small force, equals M, 2 kilograms, times A. So we have a system here, these two equations, that you would need to solve simultaneously. You can use determinants or matrices or substitution. It's the easiest way to do these is substitution. For example, on the left-hand side over here, I would just solve for T. We'd have T equals 5A plus 13. And I would take that, 5A plus 13, and plug it in here for T. So you would have 20 minus that quantity, 5A plus 13. Make sure you keep that in a quantity, equals 2A. So you can distribute the negative sign. I'll let you solve that all. Well, I'll do it partly. You're going to have 20 minus 5A minus 13 equals 2A. So what you have here is 7. Oh, this comes out pretty easy because 20 minus 13 is 7 equals 7A. So A is 1 meter per second squared. Once you have that, that's the answer to part B. You can go up and plug into some of the upper equations here, like the ones I have circled in red, and I'll circle it again in black. Either one of these two equations, you plug in the A you just found, the 1 meter per second squared, and it will give you the tension in the string between the two masses. Either equation there will give you the same answer for the tension. That would be part C.